We're now going to discuss what happens when you take a piece of p-type and n-type semiconductor and you place them together. Now, the result of this is the p-n junction, and it's something that is extremely important to modern electronics because the p-n junction is the foundation of things like diodes and transistors that we rely on to make modern processors and all other manner of modern solid-state electronics. Now, the first thing is what actually happens when we place p-type and n-type semiconductors together. Well, there's a diagram to the left here, but I'm going to draw you a little diagram here. So let's take a p-type and an n-type semiconductor in contact with each other. When they're first placed together, you know that there are an excess of holes in the p-type semiconductor and an excess of electrons, free electrons, in the n-type semiconductor. Now, because of natural diffusion processes, so particles trying to move to an area where there's less of themselves, that's called a concentration gradient. That's just sort of an interpretation of what's going on here. The electrons will start to move at this boundary from the n-type side to fill in holes on the p-type side. So we'll get a migration of negative charges over here, and they'll leave behind positive holes over here. Now, keep in mind that initially, both the p-type and n-type semiconductors are electrically neutral. Although there are holes and extra electrons, respectively, in p-type and n-type, these are balanced out by the fact that the dopant atoms have a larger nuclear charge. So because we're just adding atoms when we dope them, there's no net charge being added. They're not charged to start with. However, once we start to have a flow of charge, of electrons moving from n-type to p-type at the boundary, a charge does in fact build up, and we get a negative region here, and we get a positive region here. And you can see on this graph that creates a potential. So over here, on this diagram, we have a positive potential on the side of the n-type where the positive charge has accumulated, and a negative potential over here. So there's a potential gradient. Now, this flow of electrons across and the appearance of holes on the n-type side will continue for some time. It's called the diffusion current. Up until a point, however, where the charge differential here is actually too great for the electrons to keep moving. So if you imagine there's now an electron sitting over on the n-type side, it's going to look across the boundary and see that there's a big negative charge over on the other side. It doesn't want to go into a region of negative charge. It's negative itself. It's going to be repelled by that. And that's substantiated by this potential graph here. The electrons are not going to want to fall down the potential well to the negative region. So that diffusion current is going to decrease. Now, at the same time that's happening, so we've been talking so far about the majority charge carriers. We mentioned that term before. It's what the majority of current is going to be carried by in that material. So for n-type, that's electrons. For p-type, it's holes. There's also the minority charge carriers. So there are, of course, electrons which can move in the p-type material, and there are holes that can move in the n-type material. And this will constitute a smaller current called the drift current, which will get larger as this differential forms, the negative and positive charge builds up. Because, of course, if we have an electron over here, an extra electron that's thinking about going over to the n-type side, well, it's going to see a positive region over there. And it's going to say, great, electrons are going to want to go up the potential, and the same, a hole over here is going to want to go down the potential to the negative region. So that minority charge carrier current, the drift current, is actually going to increase. And eventually they will be the same. It'll reach an equilibrium, and the net transfer of charge will cease. So that's what happens when we form a p-n junction. The interesting thing is not so much the fact that takes place, but what then happens if we put a p-n junction in a circuit. And I'm going to show you one interesting example. You can look up other examples. For example, I've used a lot of example in that sentence. And something you could choose to look up would be transistors and how they function, or photovoltaics, which also relies on the PN junction, that's things like solar cells, that this is very interesting uses of the PN junction, but we're going to look at a simple one, which is the diode. This is just a one-way carrier of current. So let's look at how this works given the PN junction. So we have a PN junction here, and you can see that there's two ways to actually connect that in a circuit. One is with the positive terminal of our voltage source on the P-type side, and the other is with the negative terminal of our voltage source on the P-type side. Now, what you'll see is, if we connect it using the technique of number one, well, what's going to happen? By applying a positive voltage on this side, we're actually going to be reducing. Now, sorry, I missed this. What I should say is there's some terminology associated with this region that forms. It's called the depletion zone. Now, this will make sense in a second. The depletion zone is, of course, once it forms, opposing the motion of majority charge carriers. So if we decrease the width, the strength, you could say, of the potential associated with that depletion zone, we talked about that potential over here, it's going to be easier for the majority charge carrier current, which has the most potential to actually move current through the circuit, to flow, because, well, it's what is going to be able to carry the most current from the voltage source, which the voltage source is trying to move. So by attaching a positive voltage to the P-type side, we are, in effect, opposing the negative potential that is attempting to form due to the depletion zone, decreasing the strength of the depletion zone, and allowing a larger diffusion current to flow. And if you look down here at this graph at the bottom, we see that the majority of the current is actually flowing around. We get a majority diffusion current, it's now dominating again, and so we get a big net current flowing. Now, if we connect it the other way, we end up widening the depletion zone. We reinforce that negative charge, that negative potential, on the P-type side, making it even harder for majority charge carriers to flow. And the net result of that is that we end up with so the majority charge carriers have trouble flowing. Minority charge carriers can flow, but there's not very many of them, so it's not a very useful current. A small drift current moves across the barrier, but the majority of our potential to actually have a big current flowing is stopped because it can't make it across that big depletion zone. So the result is essentially no current flows. And the current that does flow is really incredibly small for most diodes that are built like this. So the net result is this configuration, current flows, and in this configuration, it can't flow to the same extent. So that is how a diode is formed. It's a one-way barrier. It's like a one-way gate for current in a circuit, and it's used to make all sorts of things. For example, used to convert AC to DC electricity, and so on. So that's the PN junction, a very useful system, and that is, hopefully you have some idea of now of how that operates.